Welcome back to Introduction to Higher Mathematics. In our last lecture, we learned about propositional logic, a mathematical way to represent how we think and reason. We discussed propositions, statements that must be either true or false. We saw how to link propositions together as we met a new cast of connectives. The conjunction, meaning and, the disjunction, meaning or. Remember that there's a difference between inclusive and exclusive or. The negation, meaning not. The conditional, meaning if-then, and the biconditional, meaning if and only if. We actually saw our first kind of proof using truth tables. And we used this new proof method to prove De Morgan's laws, which show us how to negate conjunctions and disjunctions. We talked about how to rearrange conditional statements to form the converse, inverse, and contrapositive. And finally, we learned about equivalence of propositional expressions. Well, now the moment you've all been waiting for. Today, we're going to learn how to write proofs. Before I begin, I need to mention something very important. For all but the most basic truth table proofs, there's one thing I cannot stress enough. The whole point of a proof is to convey your reasoning to a reader. So, your proofs should be written in complete sentences rather than just collections of symbols. The symbols you've learned in the last lesson for connectives are great when you're distilling a problem to its more pure mathematical form, and are great for algebraic manipulation. But when you're writing a proof, all of your little wedges and v's should be replaced with the words and or. Keep in mind one of my favorite quotes by David Hilbert. A mathematical theory is not to be considered complete until you can explain it to the first man you meet on the street. I recommend that you take a look at Guidelines for Good Mathematical Writing at this page. It's written by Dr. Francis Su, who teaches math at Harvey Mudd College, and it's got a lot of great style tips that will come in handy when writing proofs. So, let's get started. The first thing we'll need to talk about is valid arguments. An argument is an attempt to persuade someone of something by giving reasons or evidence for accepting a particular conclusion. An argument has two parts: a set of premises, and a desired conclusion. For an argument to be considered valid, the conclusion has to always follow from the premises. If the premises are true, then the conclusion must be true. We must never run into a case in which the premises are true, but the conclusion is false. Does that sound familiar? That's just like a conditional. Valid arguments can generally be based on a few basic forms. The first, most basic form is often called by the Latin phrase Modus Ponens, though it's also known sometimes as the law of detachment or affirming the antecedent. Modus Ponens can be stated formally in the following way: if P, then Q. P, therefore Q. So if you know that Q follows from P, and you know that P is true, then Q must be true as well. Makes sense, right? Let's look at an example. We'll let P represent I pass my logic test, and Q represent I am happy. So an argument using Modus Ponens would look like this. If I pass my logic test, then I will be happy. I passed my logic test. Therefore, I am happy. Now, how do we know that Modus Ponens is a valid argument? Well, let's look at some truth tables. First, we've got if P, then Q. True, false, true, true. Then we look at P. True, true, false, false. Now, since we have two premises, let's see what happens if they're both true. Let's look at if P, then Q, and P. True, false, false, false. So is this a valid argument? In other words, when the premises are true, is the conclusion true? Yes. The first line is the only one we need to look at. It's the only one in which if P, then Q, and P are both true. And when both of these are true, we can look over to Q and see that it's true as well. So our argument is valid. By the way, we can take this one step further with our truth tables. Remember that a valid argument is just a conditional statement. So let's construct one more line. This time we're going to connect the premises and the conclusion to make one big conditional. If P then Q, and P, then Q. Let's see what it comes out to in our truth table. True, 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 and finally true. Well, what do you know? It's true no matter what P and Q are. There's a special name for this type of statement. It's called a tautology. If we can show that something is a tautology, then we have proven that it's always true. The next argument form we often see is called Modus Tollens, also known as denying the consequent. Here's the formal statement of Modus Tollens. If P, then Q. Not Q, therefore not P. Remember that any conditional is logically equivalent to its contrapositive. So if P is true, then Q is true. But by the contrapositive, if Q is false, then P must also be false. Using the same P and Q as in our last example, here's an argument using Modus Tollens. If I pass my logic test, then I will be happy. I am not happy. Therefore, I did not pass my logic test. One more valid argument we need to talk about is what's called the law of syllogism. The argument goes as follows. If P, then Q. If Q, then R. Therefore, if P, then R. What the law of syllogism lets you do is chain together a number of conditionals to form one large conditional. This comes in incredibly handy when you're writing proofs, as we'll see in just a moment, because proofs often require multiple logical steps, each of which is a link in our chain. Here's an example of a use of the law of syllogism. If she weighs the same as a duck, then she's made of wood. If she's made of wood, then she's a witch. Therefore, if she weighs the same as a duck, then she's
a witch!
One word of caution. There's a common mistake that a lot of people make called affirming the consequent. Here's the flawed argument. If P, then Q. Q. Therefore, P. Can you see what's wrong with this argument? It's trying to conclude the converse of the original condition. Remember that while a statement is logically equivalent to its contrapositive, it's not necessarily equivalent to its converse or its inverse. Look at this invalid argument. If Mrs. White killed Mr. Bodie, she will go to jail. Mrs. White went to jail. Therefore, Mrs. White killed Mr. Bodie. Why is this argument invalid? Well, maybe Mrs. White killed someone else, perhaps her husband, or stole from the mansion. Perhaps she was accused of communism, which of course is just a red herring, and didn't commit a crime at all. Always be careful of these kinds of faulty arguments, which are called fallacies. Don't fall into those traps. So now, armed with the tools of propositional logic and valid arguments, it's time to get into some proofs. Usually, the thing we're trying to prove can be distilled until it's basically some sort of conditional at heart. We want to know, given some initial conditions or hypotheses, if some conclusion is true. So how do we tackle a proof like this? The most straightforward way is to assume the hypothesis and attempt to follow some mathematical steps to prove the conclusion necessarily follows from it. In other words, if we're trying to prove a statement of the form if P then Q, then we start off by assuming P and then try to show that Q must be true. This is called a direct proof. Let's see a very simple example. If A and B are consecutive integers, then the sum A plus B is odd. So, the first step to proving this is to, as we just said, assume that A and B are indeed consecutive integers. Well, what does consecutive mean? It means one comes right after the other. In other words, B equals A plus 1. Now, look at what we're trying to prove. We're trying to prove that A plus B has to be odd. Well, now that we know that B equals A plus 1, we can use that fact and replace B with A plus 1. Now our sum looks like A plus 1, which we can simplify to 2A plus 1. Now an even number is one that can be evenly divided by 2. In other words, it's a number of the form 2n, where n is some integer. An odd number, on the other hand, will be of the form 2n plus 1, since any odd number is one more than some even number. So our expression, 2a plus 1, must be odd. Since this is equal to our original expression, a plus b must be odd, as we wanted to prove. Now that we've seen the logic behind the proof, let's write it up. Assume that a and b are consecutive integers. This means that b equals a plus 1. Therefore, the sum a plus b may be rewritten as 2a plus 1, which by definition is odd. Thus, a plus b is odd. Notice a few things about our write-up. First of all, it's much more concise than our original logic. When we write a proof, it's not necessary to include every single revelation in detail. We just need to include the most important steps, the ones that lead to the solution. Second of all, notice some of the words we used. Assume, this means, therefore, thus. These are words that you'll see in the vast majority of proofs, because they help organize how one step follows from another. Finally, see that little box at the end of the proof? That's called a tombstone, and despite its scary name, it's just a cute symbol mathematicians write to signify the end of a proof. Before tombstones came into fashion, the common thing you'd see at the end of a proof, and something you may have seen before, was the letters QED. This was an abbreviation for the Latin phrase quod erat demonstrandum, meaning which was to be demonstrated. In other words, the appearance of QED at the end of a proof meant that we had arrived at the conclusion we had intended after all. Anyway, the box is fun to write, and kind of satisfying, but you can put anything you please there. A heart, a diamond, a smiley face, the Batman symbol, whatever. Pick something that suits your style. Now, sometimes you're trying to prove a statement that's in the form of a conditional, but it's rather arduous or hard to visualize. What can you do? In some cases, you can do some rearrangement and instead prove a slightly different statement that's logically equivalent to your original statement. So, what's always logically equivalent to a conditional? It's contrapositive. If you need to prove a statement, sometimes proving it's contrapositive may be easier. Let's look at another example. For any integer x, if x squared is odd, then x is odd. This proof is somewhat awkward in its current form, but let's rearrange things a bit and look at the contrapositive. For any integer x, if x is even, then x squared is even. Now this is a good bit easier to do. Think for a moment about how you do this. You can use the same definitions for even and odd numbers as the last proof. If x is even, it must be equal to 2n for some integer n. We may not know which n it is, or even if n is odd or even, but that doesn't matter. No matter what, we know 2n has to be even. So looking at the expression x squared, we can substitute 2n in for x, and we end up with 4n squared. Now factor out a 2, and we've got 2 times 2n squared. Since n is an integer, 2n squared is another integer. And no matter what integer it is, doubling it will make it even. We can actually make it a little more clear by making a new variable, say m, and letting it equal 2n squared. That way, x squared can now be written as 2m, which is also clearly an even number. So if x is even, x squared must also be even, which means that if x squared isn't even, that is, if it's odd, then x isn't even either. X is odd too. So we've proven the original statement using its much more easy to visualize contrapositive. Let's look again at the complete proof. Suppose x is even. This means that it is equal to 2n for some integer n. So x squared equals 4n squared equals 2 times 2n squared. Let m equal 2n squared, in which case x squared equals 2m. Thus x squared is even as well. I'd like to call some attention to one particular aspect of this proof. Look at our first words. Suppose x is even. This implies that rather than being some particular even number, x could be any even number. This is what makes our proof so powerful. We could try proving it case by case for particular even numbers, but I imagine you get pretty tired after a couple thousand of them. There's quite a few even numbers. But by not assuming anything else about x, other than its being even, we've proven that the theorem is true for any even number. Always keep this in mind when you're writing proofs. Finding an example that works, or 2, or 100, isn't enough to prove that it works all the time. All it takes for your proof to fall apart is a single counterexample, a case for which the proof fails. Consider the following conjecture. If n is an integer, then n squared minus n plus 41 is prime. This curious polynomial was noticed by Leonhard Euler, a Swiss mathematician and physicist, who was in fact one of the most prolific mathematicians to have ever lived. Euler noticed something peculiar about that polynomial. Plugging in positive integers seems to generate an endless supply of prime numbers. For instance, if we let n be 1, the polynomial evaluates to 41, a prime number. If n is 2, we get 43, also a prime number. 3, we get 47, 53, 61, 71. All of these are prime numbers. So had he found a polynomial that generated only prime numbers? Well, as it turns out, no. This is why I mentioned being careful about seeming patterns. If you look closely at the expression, there's a number that if you plug it in for n, you're guaranteed to get a composite number. Can you see what it is? It's 41. If we let n be 41, then 41 squared minus 41 plus 41 equals 1681, which is 41 times 41. In fact, 41 is the smallest positive integer that produces a composite number. All the numbers from 1 through 40 will give primes when plugged in. But one little counterexample makes the entire house of cards come crashing down. So our supposed theorem is false. Back to conditionals. Let's talk about something that's the basis of many of the proofs you'll see in later math classes. You've seen how to prove if P, then Q. But what about just proving Q? Where can you start? Well, that's why we have axioms. Remember that axioms are statements we can assume to be true. All you need to do is find some axiom P that leads to Q, and you've proven Q. Let's take a look at this common proof you'll usually find in an abstract algebra course. For any integer a, 0 times a equals 0. So the question starts off with the idea that a is an integer. So we'll be using the axioms that come with the integers. We'll discuss these in more detail in a later lecture. For now, just try to understand what's going on. First of all, we'll start out with the fact that 0 plus 0 equals 0. This is because 0 is the additive identity. Now we multiply both sides by a on the right. So now 0 plus 0 times a equals 0 times a. Next, we use the distributive property, distributing the a. So now we have 0a plus 0a equals 0a. Now, 0a has an additive inverse, negative 0a. So we add this to both sides. 0a plus 0a plus negative 0a equals 0a plus negative 0a. Adding a number to its own inverse gives 0. So 0a plus 0 equals 0. Finally, since 0 is the additive identity, we can get rid of it on the left side. So finally, 0a equals 0. And there you have it, proof that 0 times a number always gives 0. And all we needed was a few basic axioms that the integers have: the identity property and inverse property of addition, and the distributive property. So here's the proof. First, 0 plus 0 equals 0 by the identity property of addition. Then, multiplying both sides on the right by a and applying the distributive property, 0 plus 0 times a equals 0a plus 0a, which equals 0a. We add the additive inverse of 0a to both sides on the right. So 0a plus 0a plus negative 0a equals 0a plus negative 0a. Since 0a and negative 0a are inverses, they add up to 0. So 0a plus 0 equals 0. Finally, 0a plus 0 equals 0a, again by the identity property of addition. Thus, 0a equals 0. Now, you might be wondering, why on earth would we ever want to prove something so glaringly obvious? It's trivial, right? Sure, it's intuitive to think that a 0 times a positive number is 0. But what about 0 times a negative number? What does it mean to have none of something negative? Does it mean that you have a lot of something positive? Put yourself in the shoes of an alien first learning about your number system, or perhaps, quite realistically, a child. What seems obvious to you may not be quite so clear to them. So this is part of why it's important to be explicit in your proofs and not leave out any vital steps. So let's look at a different kind of proof. Say, like before, we have a statement Q that we want to prove. But suppose trying to get to Q from the axioms isn't really possible. Perhaps it's long and tedious, or perhaps there's no proper way to visualize it. Is there a different way? Well, there's a trick we can do. We can start off by assuming that Q is false. That is, we start off by assuming not Q. Then we follow not Q to its logical consequences, until we get a contradiction, a statement that is never true. An example of a contradiction is the statement P and not P. No matter what, one will be true and one will be false. So true and false equals false. So when something that was true suddenly becomes not true anymore in your proof, we've found a contradiction. This method is called an indirect proof. One of the first and most famous indirect proofs was Euclid's proof that there are an infinite number of primes. Here's how his argument went. Suppose, rather than there being an infinite number of primes, that there are only a finite number of primes. That means we could list them out. Call them P1, P2, P3, and so on, all the way to Pn. And we'll say these are all the primes. Now, if we multiply all the primes together, then we have a number that's evenly divisible by P1, P2, P3, up to Pn. Now here's the fun part. Take that number, add 1, and call it m. Is there a prime that divides evenly into m? Well, it can't be P1, because m is 1 more than a multiple of P1. It can't be P2, because m is 1 more than a multiple of P2. In fact, none of our primes can divide evenly into m. It's 1 more than a multiple of each of them. So there must be some other prime not in our list that divides evenly into m. But wait, didn't we just say that P1 through Pn was all the primes? Yet now we've got a new one. There's our contradiction. So, since assuming that there's a finite number of primes leads to a contradiction, there must be an infinite number of primes. Why does this trick work? Let's take a look at it logically. We're saying that if a statement Q is not true, then we'll end up with a contradiction. We can represent this in the language of logic as if not Q, then contradiction, which we often just notate with an F because a contradiction is always false. Now, this statement is logically equivalent to its contrapositive. But what's the negation of a contradiction? A tautology, of course. The opposite of false is true. So the contrapositive reads as if tautology, then Q. And since a tautology is true by definition, by modus ponens, Q must also be true, and Bob's your uncle. Now, sometimes, rather than needing to prove a statement by itself, you need to prove some combination of them. Perhaps a conjunction or a disjunction. So let's see how to prove each of those. It's pretty easy to see how to prove a conjunction. Say you have to prove P and Q. Just prove P and then prove Q. You have to prove each one separately. For instance, let's say we wanted to prove that every multiple of 6 is divisible by both 2 and 3. First, you'd have to prove that every multiple of 6 is divisible by 2, and then separately prove that every multiple of 6 is a multiple of 3. I won't go into the actual proof, but you're welcome to try it on your own. It's pretty easy. Now, as for a disjunction, those are a bit trickier. There are 2 pretty useful ways to do it, though. The first way is to break up your problem into cases, and show that some cases prove P, and some cases prove Q. If these cases are exhaustive, that is, if they account for all possibilities, then you've proven P or Q. For example, consider this theorem. For every integer x, the remainder when x squared is divided by 4 is either 0 or 1. So we might see, after trying a few possibilities, that whenever x is an even integer, the remainder when x squared is divided by 4 is 0. And whenever x is an odd integer, the remainder is instead 1. So we can use that. Suppose x is even. Then it can be represented as 2n for some n. And so x squared is 4n squared, which is a multiple of 4. So its remainder when divided by 4 is 0. Now suppose x is odd. Then instead we can represent it as 2n plus 1 for some n, making x squared equal to 4n squared plus 4n plus 1. This is 1 more than a multiple of 4. Can you see why? Then the remainder, when we divide it by 4, will also be 1. So we've taken care of evens, and we've taken care of odds. That pretty much covers everything, doesn't it? So we've managed to prove that no matter what integer x is, the remainder when we divide it squared by 4 must be 1 or the other, 0 or 1. The second way to prove a disjunction is a little more clever. Remember that for P or Q to be true, at least one of P or Q has to be true. So what if we already know that P is false? If we want P or Q to be true, then Q had better be true. This lends itself to another proof method. To prove P or Q, assume P is false, that is, assume not P, and show that Q must be true. Take a look at this one. For every real number x, if x squared is greater than or equal to x, then either x is less than or equal to 0, or x is greater than or equal to 1. So, we start off by assuming that x squared is greater than or equal to x. Now, suppose x is not less than or equal to 0. This means it has to be greater than 0, strictly positive. So, if we divide both sides of the inequality by x, we don't have to swap any signs. X squared divided by x is x, and x divided by x is 1. So x is greater than or equal to 1. And there you have it. Either x has to be less than or equal to 0, or x has to be greater than or equal to 1. Mission accomplished. Alright, one last proof method we need to go over, but this one will be quick because of what we've already learned. We've seen a wealth of ways by now to prove if-then statements. But even stronger than if-then statements are if and only if statements, biconditionals. So the question is, how can we prove a biconditional? Well, remember that a biconditional is actually equivalent to two conditionals in one. If P then Q, and if Q then P. So this is a conjunction. And how do we prove a conjunction? Prove each part separately. In other words, to prove a biconditional, we need to prove if P then Q, and then prove if Q then P. We prove the conditional, then its converse. But wait, there's even more we can do. That second conditional, if Q then P, is equivalent to its contrapositive, if not P, then not Q. So if we can show if P then Q, and then show if not P then not Q, that proves our biconditional too. Instead of proving the converse, we prove the inverse. In fact, we can replace either of our two conditionals with its contrapositive and the proof will still be valid. How many ways do you think there are to do this? So while they may seem daunting at first, biconditionals are actually one of the easiest types of statements to prove because of their flexibility. Use whichever rearrangement of if P then Q and if Q then P seems best suited to the proof at hand. I'm going to pose a small challenge to you. Let's take one of the theorems we talked about earlier and make it a bit stronger. For any integer x, x is odd if and only if x squared is odd. See if you can prove that. Good luck. Next time, we'll be leaving logic for a while to explore another topic found throughout mathematics, sets. See you next time.